Hello, I'm Michael O'Connell, and in today's video we're going to be performing a torque balance on a Couette viscometer. A Couette viscometer is a unique device that can be used to find the viscosity of a liquid. So I'd like to describe it to you first. I drew a small picture up here, and basically I'll describe what I've drawn. Basically, we're going to have a Newtonian fluid, and I'll explain the importance of that in a second, in between two concentric cylinders. Where the inner cylinder is attached to a shaft, we're going to exert a force, or a torque, on that shaft to spin our inner cylinder. The key thing to understand here is that the outer cylinder will remain stationary and needs to remain stationary. But in order for that to be the case, the torque needs to balance. It's just like if I have contents in a small cup, and I stick my finger in and mix the contents around without holding the cup. The cup begins to spin along with my finger because the contents in the cup are in contact with the cup and spinning due to the torque exerted by my finger. It's the same scenario here with our Couette viscometer. The shaft spins the inner cylinder, which is in contact with the Newtonian fluid in between the concentric cylinders, and because that fluid is in contact with the outer cylinder would begin to spin. But we can't have that happen if we want to determine the viscosity of that Newtonian fluid. In this case, it would be a liquid like water for us in this video. So why is that the case, or how is that the case? What does that mean for this velocity profile here, this crazy equation that we're given? And those are all great questions, and this is why I want to describe the no-slip boundary condition, which assumes that the velocity of a liquid at a surface is equal to the velocity at that surface. And you're probably like, oh my gosh, word salad, that makes no sense. Which is the same reaction I had the first time I was taught this. So let me try to describe that to you. Let's draw a top view of our concentric cylinders in our Couette viscometer. So basically we have fluid and it is just spinning around, right? Because we have that inner cylinder moving. But as I said, this outer cylinder here is not moving. And then this inner cylinder is spinning at some velocity, right? And hopefully you remember from physics, that would be the velocity would be equal to the product of the radius of the inner cylinder and its angular velocity. Again, all of that would be dictated by the torque that we're exerting. Okay, so the no-slip boundary condition. So the velocity of the liquid at the surface is equal to the velocity of the surface. So that means our inner cylinder that's spinning at Ri times R sub I should say, multiplied, that's the inner radius multiplied by the angular velocity. That is also the velocity of the liquid that's spinning around. So the velocity of our surface of the inner cylinder is equivalent to the velocity of the liquid at that surface. So what would that mean for the velocity of our liquid at the surface of the outer cylinder? Hopefully you realize that that would be zero. The velocity would be zero because our outer cylinder is not moving. So if the velocity of the surface is zero, then the velocity of the liquid at that surface is zero, assuming the no-slip boundary condition holds. So what are we going to be doing in this video with this torque balance that I mentioned and seem to not have talked about since? Basically, we have these three equations. I want to talk about those really fast as well before we get into balancing the torque. This is going to be the velocity profile. So that is going to be, as I said, I shouldn't have erased it, but with this concentric cylinders, so if the velocity of the liquid is zero at the outer cylinder and it's the inner radius times the angular velocity at the inner cylinder, what is it in between? That's what this equation describes with respect to the changing radius. So that would be some distance between, our concentric cylinders. How is that velocity changing? Obviously, as we move closer to that outer cylinder boundary, which is stationary, our velocity is going to be decreasing. And that's what this equation describes. And that's going to be very important for us in demonstrating that the torque on the inner cylinder is equal to the torque on the outer cylinder. So you might ask, well, why is that necessary? And as I described before with the finger mixing the contents in a cup example, we need the torques to balance. Basically, we need to exert a force on our outer cylinder to counteract the torque that we're exerting up there on our shaft, such that the outer cylinder remains stationary, such that we have the no slip boundary condition that we apply to this problem. And then that would allow us to use the Couette viscometer to find the viscosity of our liquid. But in this case, we just want to demonstrate that those torques balance. And what that actually shows is that this velocity profile equation that's given to us and this shear rate equation that's given to us are legitimate. They're valid. They work, which is great. This constant K is the ratio of the inner radius, that's the radius of the inner cylinder, to the outer cylinder. Okay, and you see that in our velocity profile equation. The last thing I want to talk about before we start getting into doing the torque balance is Newtonian fluid. So if we have a Newtonian fluid that's a liquid like water in between our concentric cylinders and we're measuring the viscosity, then Newton's law of viscosity applies. Now, torque is usually denoted with tau, and shear stress also happens to be denoted by tau. So I'm going to actually use a different variable for shear stress, and I'm just going to randomly choose lambda for this video. Okay, just because I don't want to be mixing up those terms. But we're describing Newton's law of viscosity, which states that the shear stress, so that would be a stress that's applied along a surface. So just as our torque would be, so if we're spinning that shaft, notice that our surface is that inner cylinder, right? So it's like parallel, it's along the surface of the cylinder. That's where the stress is being applied. Unlike the normal pressure forces we're used to dealing with, which are normal to the surface. Okay, so we have lambda, that's the shear stress, and that is equal to the product of mu, which is going to be the viscosity of our liquid, multiplied by sigma, and that is this. That is the shear rate. Okay, and that is going to be very important for us when we do this torque balance. So with that, I think we're ready to begin. I would like to begin describing the torque on the inner cylinder because the inner cylinder is the one that's actually moving. So it's a little more interesting. At least it would be in real life, but it really doesn't matter, honestly, which one you choose. So I'll denote that as tau sub I. Okay, and we all know the torque equation, right? So this would be the radius of our inner cylinder multiplied by whatever force we're exerting that's perpendicular to that radius. Okay, so what about force? Well, again, I talked about shear stress and pressure and the difference between the two, but the units are the same. Okay, so what that means for us is that for our shear stress lambda, that's still just like normal pressure, it's force over area. So we can plug that in there, which means that this is the inner radius multiplied by lambda, which is our shear stress, multiplied by the area of contact. And we'll derive a very quick expression to describe the area of contact between our fluid and the inner cylinder later. But the reason I don't want to do it now is I don't want to crowd up the board with too much just yet. Okay, what about lambda? Well, I just described an equation for lambda. In this case, we're dealing with a Newtonian fluid for our liquid. So his law applies there. So we have the viscosity, which we can take to be known at this point, and then we also have the shear rate. And that's where these two equations that were given to us at the start, this is why they matter, because the next thing we're going to have to do, so we substitute this into here, right? So we have a new equation now. Hopefully you can see this. Yeah, you have the inner radius. Oh, we don't need an equal sign yet. Okay, multiplied by the viscosity of the fluid, multiplied by the shear rate, multiplied by the area of contact. Okay, so that's the torque on the inner cylinder. The next thing we have to do is we have to find this sigma. What is this shear rate? Like, what would that be? Okay, and this is where, as you can see in the shear rate expression, the velocity profile equation goes into this. And then we have to take a derivative and do some other stuff too. Okay, so remember this equation. If you're taking notes or something, write this down. Okay, so this is the inner radius multiplied by the viscosity of the liquid or the fluid, multiplied by the shear rate, multiplied by the area. Okay. We're going to erase all of this temporarily so that we can find this shear rate. We need an expression for the shear rate with things that we know. Okay, so let's start in here. We have our velocity profile equation divided by r. So this would be 1 over r, and we can distribute that in, which would make our velocity profile equation still have your angular velocity, those ratios, the k constant that we had before. Hopefully you wrote that down. Then this is going to be r squared over r squared minus 1. Okay, what do we do next? We derive with respect to r, and this is pretty good, right? Because again, these k, this is the ratio of the inner cylinder radius to the outer cylinder radius, so those are known. We are going to know the angular velocity, or I should say, I think it's the radial velocity, because this is the angular velocity I think we would be describing, so sorry about that. This would be our radial velocity in like radians per second or inverse seconds. It's described in different ways, obviously. Revolutions per second is another one. This is pretty easy to derive. We're deriving with respect to r. All we have is r down here. That's just like if you were deriving, it is in the denominator, so it'd be like r to the negative second, right? So you bring down your negative second, right? And then it would be this, right? So it'd be negative 2 r to the negative third. Okay, so that's not too bad, right? That's not too scary. So p theta, so we would have negative 2 and then here, okay, this term here is constant, right? I forgot about this. And it's multiplied by negative 1. What's the derivative of a constant? It's 0. So that goes away. Okay, cool. So we have this large r squared. If I didn't make it clear already, large r, that's the radius of our outer cylinder. And then our independent variable, r cubed, right there. Okay, the next thing we do there is we're going to multiply by r. Okay, so we've taken the derivative. So that's pretty simple. All of that does is that just makes this, hopefully you see that, this becomes a 2, right? So this is r squared. This is really good for us now, right? Because now we have an expression, and I am so sorry, big mistake that I made here, to be careful, is I need to be careful what I'm writing on this left-hand side of the equation, right? Because look at this equation. This is correct math on the right-hand side, but this is wrong. Because we've been performing this. Does that make sense? So this is sigma. So I'm just pointing out my errors as I go, because when you're doing this, you need to be paying more attention than I'm doing. So this is sigma. Okay, this is our shear rate. Now, if we're thinking back to that equation we had for the torque on the inner cylinder, right? It was the inner radius, viscosity of the fluid, multiplied by sigma. And then I'm going to put sub I because it's the shear rate for our inner cylinder multiplied by the area of contact. Okay, that's super important. So this would be sub I. Now what does that mean for, I should say, the independent variable, r? Well, that means it's Ri. Now why is that important? Well, if you look here, so if this radius squared under here, hopefully you see, if that is the inner radius, so we have the outer radius squared over the inner radius squared. Oh man, that's something really, really important, isn't it? Because think of that. We know that K is what? K is the ratio of the radius of the inner cylinder over the radius of the outer cylinder. So if this was flipped, so if it was the inverse of K, then it would be that, and then we could square it. So it would be the same, right? So if we took k to the negative second, it would be, so we would flip this fraction, it would be r over ri. So the radius of the outer cylinder over the radius of the inner cylinder, and then again, it's to the negative second, so this would be squared. That's the same thing we have here, okay? So that's fantastic, right? So what does that mean for us? Well, that means that this term is k to the negative second, right? Another mistake I see that I've made here, again, being careful with exponents. This is squared too. So if this is k squared, and this term here, this, is k to the negative second, then those cancel, okay? So that leaves us with this equation that I'm going to write. I'm just going to erase some of this so that you can see it. This equation for the shear rate at the inner cylinder would be, we have our -2 multiplied by the radial velocity. Now that those canceled, it's just 1 over 1 minus k squared. Okay, excellent. And then that goes into here, right? That goes in to our equation for the torque exerted on the inner cylinder. Excellent. Okay, we're really in the home stretch here, I promise you. So we need to rewrite this expression. So now I think, because I've definitely already committed the crime of taking up a lot of space on this whiteboard, so hopefully you're able to follow along. Now that we substitute that in, we can rewrite this equation. And that is going to be the torque on the inner cylinder is equal to the inner radius multiplied by the viscosity of the fluid multiplied by the shear rate at the inner cylinder, which is going to be -2 times the radial velocity over 1 minus k squared, where k is the ratio of the inner cylinder radius to the outer cylinder radius multiplied by the area of contact. So you probably know where I'm going to go here. The last thing that we want to do here is describe that area of contact, which is not hard. There's no reason to overthink this. So we have our fluid moving around the inner cylinder. Remember, we're describing the inner cylinder. So it's moving around in a circle. We remember what that is, right? The perimeter, that's the circumference, right? So that'd be 2 pi times the inner radius. Okay? And then, well, how high, right? How high? Well, I don't really know. We'll just say h, right? We need to know the height of our cylinder, because that would be the area of contact, so that would go into here. Okay, so that leaves us with this final expression. And then notice we could have an RI squared. We can pull 2 times 2 up front. So I kind of like to do stuff like that. So we could say -4 pi. Let's cross stuff out as we use it. And then we'll have mu up there, the viscosity. We use that. RI squared is up there. So that's the radius of the inner cylinder squared. So those are gone. We have the radial velocity based on the torque that we're exerting on our inner cylinder up from the shaft, multiplied by the height, and this was substituted for the area. So that's gone all over 1 minus k squared. Okay, again, write this down, okay? Because we need to make sure that the torque on the outer cylinder is actually equal to this. So how would that look like? What would that look like? Okay? So what we would want to consider here, again, is this term, right? Now we want to find sigma sub O, where that would be the shear rate on your outer cylinder. We're trying to find the shear rate for the outer cylinder. And I said that this would be equal to the shear rate on the inner cylinder. Is this correct? And the answer, of course, is no. So I was already kind of heading in the wrong direction here. So I kind of want to correct that. Now let's maybe think about why that isn't the case. Well, it's actually pretty simple, because I spent the first part of this video talking about the no-slip boundary condition. So obviously at the stationary surface at the outer cylinder, the velocity is not going to be the same as it is at the inner cylinder. Okay, so the shear rates definitely aren't going to be the same, right? Because again, the shear rate depends on that velocity. Okay, so what we need to think back to is the thinking that I had is correct, right? We want to use that same expression that we had for the shear rate at the inner cylinder, which I believe was -2. We had the radial velocity again. We had k squared over 1 minus k squared multiplied by r squared over little r squared. And remember, the big revelation that I had that we talked about there is that this r, the independent variable for our inner cylinder, was r sub I, right? It's the radius of the inner cylinder. We figured out that this term is k to the -2nd power, such that these canceled, and everything was amazing. But what would happen if this was for our outer cylinder? What about the shear rate for the outer cylinder? Well, the equation would be the same here, right? Those terms would be the same. It's all about that independent variable, r, which is just where we are. Again, that's why you can say that this is like the shear rate coordinates, right? Because it's dependent on this variable r. Because it's all dependent on where we are in the fluid that's between these two concentric cylinders, right? If we're closer to the inner cylinder, that fluid's moving faster, right? If we're farther away, closer to that stationary boundary, that outer cylinder, we're not going to be moving as fast. Okay, so this r would be big R, right? So let's write that so you see that this cancels out. So we have our k squared over 1 minus k squared. All of that was constant as before. But now, our independent variable r, our location, is O. We're at the outer cylinder boundary. So that's the larger radius. So r squared over r squared is 1. And that goes away. So hopefully you see that there. So for us, this is actually going to be the shear rate at the outer cylinder. Okay, this is quite chaotic. Right? Okay, so we're going to do the same thing that we did before up here. This time, these are all O's. This is a big R, blah, blah, blah. I'm going to rewrite all of this. Okay? And basically, hopefully you wrote down the equation from before for the torque on the inner cylinder, and we're going to show that this is going to be equal to the torque on the outer cylinder. Okay? So our torque on the outer cylinder, if we modeled it after the equation we had for the torque on the inner cylinder, would be large R this time, right? Radius of the outer cylinder multiplied, of course, by the viscosity of our fluid mu, multiplied by the shear rate at the outer cylinder, multiplied by the area of contact. Okay, so what would the area of contact be this time? Hopefully you realize it's the same idea, right? Circumference, 2 pi r, and then the same height, of course. Okay, so all the height of the fluid that's in contact with the outer cylinder this time. Okay, so we plug sigma in, right? So let's pull out the r there. We have that. Okay, what was this? This was -2 times the radial velocity times k squared over 1 minus k squared. And again, this is that term there. That's what this is. And then, okay, we got rid of that, so we have 2 pi h. Ooh, okay, what does this look like here? Right? Little nervous, right? Doesn't look exactly the same. You're kind of wondering, like, did we do something wrong? This doesn't, we had like r sub i's and stuff like that before. All legitimate concerns. There's one way that we can remedy this. Before I do that, let's make it look like it did before, right? So let's re-describe this, right? Put the negative in front. 2 times 2 is 4. We'll put the pi in front again. We'll put the viscosity in front again. Stuff like that. We can put the radial velocity up there too. Okay, so that's gone. Okay, and let's put h up there too. Okay, what are we left with? Well, we're left with r squared times k squared over 1 minus k squared. Well, we remember we had the 1 minus k squared in our denominator for our expression for the torque on the inner cylinder. So that's good that we have that for the torque on the outer cylinder. But we see this multiple, r squared multiplied by k squared. This is better than you think, right? We know what this is because we know that k is equal to the ratio of the inner cylinder radius to the outer cylinder radius. So if this is squared, right? Oh, look at that. Those go away, and then you're left with Ri squared. So this is Ri squared again, and this is 1 minus k squared. If you check your notes, I just keep making like really silly things, getting too excited, right? It's not quantity 1 minus k squared, it's 1 minus k squared, okay? And if you check, that should be the exact same equation or expression that we had for the torque on the inner cylinder. I'll move a little bit out of the way so that you can see that. But I think that's pretty cool. And again, if I didn't emphasize this already, you might be wondering, why is this important? Why is it important that the torques are equal? I think I did demonstrate that a little bit with my finger spinning the contents in a small cup, right? In that case, it's important for the torques of the balance, aka you need to hold the cup while you spin your finger in there so that you don't spill the contents of your cup everywhere on your table and on your desk and all of that. So you understand that for that, but what about your Couette viscometer? Why is it important for that? Well, it is important because these equations, right, this velocity profile equation and this shear rate coordinate equation, what this states, if these torques balance as we've demonstrated, then these two equations are valid. They're able to be used. And then you might be wondering, well, okay, why is that important? Well, of course it's important because the whole point of the Couette viscometer is it's to be used to find the viscosity of the liquid that's between these concentric cylinders, and you can't do that if your velocity profile equation that you have modeled here is just garbage, if it's just wrong, you know? And similarly, of course, if your shear rate coordinate expression is also incorrect, you're not going to be able to find an accurate viscosity of your liquid. So that's why the torque balance that we've performed here on the Couette viscometer is important for this video, because you need to demonstrate that the torques balance such that these equations are true, such that you can use the viscometer to actually find the viscosity of your, in this case, Newtonian fluid or some liquid in between those concentric cylinders. So there's kind of a lengthy explanation there at the end as well. I hope you enjoyed this video. I hope you were able to find this somewhat followable so that you could follow along and figure out how we derived these expressions and showed that the torques balance. But thank you so much for watching, and I'll see you next time.